Welcome to the survey of the elementary principles in classical mechanics. Today we are going to discuss velocity-dependent potentials and the dissipation function. If a potential does not exist in the usual sense, equation 157 still follows from a function u, depending on the generalized coordinates and the generalized velocities, such that the generalized force is given by the expression here, and the Lagrangian is just the kinetic energy minus this function, which we'll call a generalized potential. And you can check that if you start from the general form of the Lagrange equations and you introduce the generalized force with this definition, it follows immediately that you obtain the Lagrange equation for the usual function, but containing u instead of v. So as already mentioned, u is the generalized or velocity-dependent potential, and it is employed in classical electrodynamics, where it describes the forces exerted by an electromagnetic field on electrical charges. If a charge q of mass m and velocity v moves in a charge-free space where the electromagnetic field E and B is present, the charge experiences the Lorentz force. This is something that we've already discussed in a previous video. The element of novelty for today is that we can express the electric and magnetic induction fields in terms of scalar and vector potentials. So E can be written as minus the gradient of a scalar potential minus the partial time derivative of a vector potential, and the magnetic induction can be written as the rotor of the vector potential. And these things follow from general considerations in Maxwell's equations. The electromagnetic field is a continuous function of time and position derivable from scalar and vector potentials. So the generalized potential, in this case, the function u, is given by this expression. It's the charge multiplying the scalar potential minus the charge multiplying the dot product between the vector potential and the charge's velocity. With a Lagrangian of the form t minus u, the expression is the one here. And now in order to construct the Lagrange equations, I'm going to employ a few shorthand notations. The partial derivative symbol with a letter index with no dot above means that I'm taking the partial derivative with respect to the j Cartesian coordinate. So this could be x, y, or z, or coordinate 1, 2, 3, depends on how you want to label them. And if I use the same symbol but the index has a dot above its head, it means I am taking the partial derivative with respect to the velocity corresponding to that coordinate. So for example, for the partial derivative with respect to coordinate j, the result is clearly this term does not contribute anything. Over here I have just a partial derivative of the scalar potential, and then I apply the operator to the dot product, which I write here in the summation convention. So this is just assumed to be a1 times v1 plus a2 times v2 and so on. So it's just the dot product expanded but written in a compact form. So this is the derivative with respect to the coordinates. If I now take the derivative with respect to velocities, I will retain a term from the kinetic energy, and then I also get a term from the dot product here. It's obvious that I'll end up with a contraction on the velocity, so then the delta symbol and summation over the k index will leave the j component of the vector potential standing, And then I can take the total time derivative of this expression, which yields the acceleration. Then this is just the expansion of the derivative for the vector potential in terms of the Cartesian coordinates and Cartesian velocities. And then there's the partial time derivative of the component. So from these two results, I can leave the Cartesian component of the acceleration on one side and throw everything else on the other side. And you can see that with these two terms, I can come here, and these other two terms are grouped here. And now, so it's this one and this one. And now if we look at our previous definitions for the fields in terms of potentials, I'll bring them back up a second, so these two. It is clear that the J component of the electrical field is simply given by the expression here, so it's exactly what we found in our first bracket. And now for the J component of the cross product between velocity and magnetic induction, since this is a cross product, I can write the component using the Levi-Civita symbol. So it's an epsilon jki of component k of the velocity and the component I of the magnetic induction. But given the magnetic induction known definition as a rotor, the I component will just be an epsilon ILM partial derivative with respect to the L component of the L coordinate with respect to the M component of the vector potential. And then it is clear that with an even permutation, you can bring the I index on the first line here, and then summing over it, you contract the Levi-Civita tensors. You obtain a sum of two terms involving delta functions, delta Kronecker deltas, and if you then contract the sum over them, you end up with the result here. It's very straightforward. And this is exactly what we obtained above. So in other words, this component of the acceleration multiplied with the mass is equal to charge multiplying the J component of the electrical field plus the J component of the cross product between velocity and magnetic induction, but this is just the expression of the Lorentz force. So in effect, using this potential, this generalized potential, we have obtained Newton's equations. Now, the electromagnetic field is invariant under a gauge transformation. So if I have a set of initial potentials, vector and scalar, I can transform them as follows. The vector potential has added the gradient of some scalar function psi that can depend on coordinates and time, and the scalar potential is added with a minus sign. Has added the partial derivative of psi with respect to time. If I write the Lagrangian with these new potentials, so I start from its definition and I just include these new functions and work things out, I obtain a new Lagrangian L prime that is equal with the old one plus the charge Q multiplying the gradient of psi in a dot product with the velocity plus the partial derivative of psi with respect to time. But this is just the total time derivative of q times psi. So in effect, I have obtained a Lagrangian L prime equal to the original Lagrangian L plus the time derivative of a gauge function. The conclusion is that the dynamics of the charge is unaffected by a gauge transformation of the electromagnetic field, because as we've already seen, this transformation of the Lagrangian leaves the equations of motion invariant. It can happen that not all forces are derivable from a potential, but even in this situation we can still write a Lagrange equation uh, in the context in which L is going to contain the potential of the conservative forces. So this is still going to be T minus V, and the generalized force is going to represent forces that do not arise from a potential. Such situations occur when dissipative forces are present, as for example are velocity-dependent forces. And this is an example of a force that depends on the velocity a particle has in a given direction of space through some dissipation or a friction constant. And such a force arises from what is known as Rayleigh's dissipation function, which is this calligraphic F equal to 1 over 2 times sum over I, where but the index I now assumes that I have a many particle system, so I'm summing over particles, and in each case I'm summing over the squared component of the velocity of each particle, and I multiply with the dissipation constant. And it is clear from these definitions that the velocity-dependent force is minus the gradient of the dissipation function, but it's a gradient with respect to velocities and not coordinates. To understand the physical interpretation of the dissipation function, we need to look at the work done by the system against friction. So if I take an element of work done against friction, this is just minus times the dot product between the frictious force and line element, which can be written as velocity times a differential element of time, but then I can write the force as the gradient with respect to velocities of the Rayleigh function, and then if I work it out, the immediate result is that I get this expression, which is just twice the dissipation function. So the rate of energy dissipation due to friction is twice the Rayleigh dissipation function, which is the result here. And now if you look at the definition of the generalized force and you write it for a velocity-dependent frictious force, then you can very easily work things out and obtain that Q is minus the partial derivative of the Rayleigh dissipation function with respect to of the dissipation function taken with respect to the corresponding generalized velocity. An example of such a force is given by Stokes' law, where a sphere of radius a moving with a speed v through a medium of viscosity eta experiences the drag force given by minus 6 times pi times eta times the radius a times the velocity of the sphere. And the Lagrange equations of dissipation are then simply the left hand side remains the same, but if we move Q from the right to the left, then we need to flip the sign here, so it's just plus this partial derivative of f. So for such systems, we need to know two scalar functions in order to determine the equations of motion. Namely, we need to know L as a function of kinetic energy and conservative potentials, and the Rayleigh dissipation function. In summary, we have defined the velocity-dependent potential and have exemplified its use with basic applications in classical electrodynamics. We have discussed dissipative phenomena in terms of the Rayleigh dissipation function and have constructed the Lagrange equations for systems with velocity-dependent dissipation. In the following, we will present simple applications of the Lagrangian formulation of mechanics. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.